Dr. Cordino, so today's content is the last content for exam, or should we more take it like Friday? Or,
The exam's on Wednesday, so
Yeah.
I guess so. So do you think that I'm gonna be giving you an exam and be teaching you stuff that's gonna be on the exam while you're taking the exam?
Probably not.
Okay, well,
He means the last Friday.
Yeah, last Friday.
he'd be putting out the
Last
last.
Friday.
Oh. What you said today?
No,
Okay.
Is today's the last content, or
Is
with
Yeah,
Friday?
but I don't think it's gonna make that much of a difference, because what I wanna do today is mostly kind of slog through some of the details
Okay.
of stuff that we've done before. So there might be a new lemma or two, but the big picture is not gonna change between Friday and today, so. Yes, the review session, assuming everything goes without a hitch, because actually I didn't let Lynn know until Friday morning. Of course, that was the day of the calculus challenge. But according to 25.5, the room I asked for is open, so there we go. If for some reason it's not, just meet up in my office and we'll figure out where to go. And if you're late to that, I'll leave a note on the door, so, but it's all gonna be good. Okay, so I had, last time, I had two very similar lemata toward the end. This was the first one, where you start off with the fields and, you talked about, comparing, the indices of the groups with, the degree of the field extension. There's another one where you start with the groups and compare the, degree of the field extension with the indices of the groups. The proof of this is very similar to this. I'm only going to do this one, and the analogous result is the last thing that I did as far as showing what it was. But this is kind of a fun proof. So I can go through it a little bit before we just stand the heat off. So what this says is you have these extensions of fields with L inside M. If the degree of M over L is finite, then the index of L of M prime and L prime is bounded above by the degree of this extension. And so this falls pretty easily. This is the big piece here. What we're going to do is we're going to go by induction on the degree of M over L. We're going to go by induction of on the degree of the extension. Right. Note that so notice, of course, in the base case, for n equals 1, then of course, if the degree of this extension is 1, then that means M and L are the same thing. And so this certainly happens. And it's easy to see that if you look at the group of automorphisms that fix M, that's exactly what fixes L, right? Because they're the same fields. So in fact, we have equality here, right, in this case. So that takes care of the base case. Now, suppose that n is bigger than 1, we will assume the conclusion for all I that's less than n. All I strictly less than n. I'm going to reduce this to a simpler case. And by a simpler case, what I mean is the case where, in fact, M is a simple extension of L. And the way I want to do this is as follows. Let's select U And certainly there must be some such U because, we're assuming that, n is bigger than one, right? And notice that the degree of m over L is degree of m LU over L. Of course, let me point out that U is algebraic, right? Because the extension is finite. U is algebraic over L because, of course, the entire extension here, M over L, is finite. So in particular, any element of M is algebraic over L. With minimal polynomial f of x. Now, so notice that the degree and the degree of M over LU is N over K, right? So in this case, notice that L prime over M prime is equal to L prime over prime LU prime over M prime. And by induction, this is less than or equal to well, unless perhaps K is equal to N. Right, because if K equals N, then that means that this is, did I get this turned around? Yeah. I mean, that's right, but if K equals N, then that means that this right here is one, and I can't really use the induction hypothesis. So now I have to get over that hump here, where what happens if K is equal to N? And this means we have M is equal to LU. So we have reduced to case in which M is simple. Well, right. So how do we proceed in this case? In this case, what we're going to do is we're actually going to construct a one-to-one map from the set of left cosets of M prime and L prime. We explicitly construct a one-to-one map from the left cosets of M prime and L prime to the set of distinct roots of F and L. Um, so I meant, not that. M. And of course, notice that this set is bounded above by N equals the degree of M over L, which is the degree of F of X. Because F of X was the irreducible polynomial of U, and of course U is one of those roots in M. But of course, we're in the case now where M is equal to L of U, it's the entire extension. So that means that this degree here is N, and that's the same as the degree of this polynomial. So the set of roots in M is bounded above by the degree of this polynomial. And actually, there's something here in this proof that is kind of going on in the background that's going to be important for us in the future. Notice that I did say the distinct roots here. I did, didn't I? Yes. And this is going to be an important feature of this. We're going to call this set I'm going to call this set S. I'm going to call this set here T. And I'm going to define this function from the set of left cosets as follows. Let tau n prime be a left coset of M prime and L prime. And let sigma be any element of the Galois group of F over M. Now remember what M prime is this is the set of all automorphisms of F that fix M, and that's what's going on. So sigma is in the Galois group. This is another way to call this M prime, the automorphisms of F that fix M. So if you look at tau sigma U, tau, look at tau sigma U, where U is the generator of that extension. This is equal to tau U. anybody explain why?
Because you was an M.
Okay, that's right, because U is an M, so sigma leaves that alone. And so essentially that's just U, right? So that's all this is. And so what this means, there's a consequence to this. We're building up to constructing a well-defined map. It means that every element of the coset tau m prime has the same effect on U. That is to say that tau sigma of U is tau of U. No matter what's in that coset, it takes the same place. And this allows us to find this map. A map from S to T. My input is going to be a left coset, which I could call tau m prime. And this needs to go to one of the distinct roots, and this goes to tau u. This map is well defined by the argument we just had, because it doesn't matter what coset representative tau that I take, it always gets the same effect. So this is a well-defined function. We need to show that it's one-to-one. So suppose that tau u equals tau 0. That'd be given. So in other words, this is the image of the coset tau m prime, and this is tau 0 m prime. Yes.
Are we modding, so is S equivalent to L prime mod M prime?
But it's normal.
Hmm?
Nobody says it's normal, so
Oh.
I'm looking at this, let's go. Right, so suppose that, let me call this map something, just make it better. So suppose this happens, well, this means that tau inverse tau u equals u. And this means that tau inverse tau well, that's a rather bold claim, isn't it? Right? Pretty bold of me, isn't it? Just to write this down for one element. Oh, look, tau inverse, tau 0 inverse tau fixes u, and then I'll make the bold claim that it fixes everything in M. All of you game. Remember, in our case, M is LU, right? So any automorphism of M that fixes U has to, because it's automatically going to fix L, right? Everybody okay with that? So this fixes all of M. Therefore, okay, so this function is in fact 1-to-1. And there we go. So there exists a 1-to-1 function from the left cosets of M prime and L prime to distinct roots of fx. And this is less than or equal to n. Therefore, these number of left cosets
Dr. Gordon,
mhm.
what is, tau is part of L prime? Tau is in L prime?
Yes, that's right.
Okay.
That's right.
Why is tau of u a distinct root, like a root of f of x?
Okay. Well, here's why, because, so notice that, we're gonna call it S into T. So. That's the way the. Suppose you have, let's suppose. Oh, it has to be distinct because of the 1-to-1 is here, right?
No, but I'm saying why is tau of u a root of f?
Because it fixes L, right? That's true for any automorphism. So f of x 0 plus a1 x plus a2. And Lx. So each of these AIs are in L.
Mhm.
So they're ignored by tau, right? So suppose u is a root. Okay, so when I apply tau to this.
Right.
So tau u is also a root, right?
And just also tau is in L prime, which is the Galois group, I think.
Mm-hmm. So is that clear?
Yeah.
Okay. All right.
Dr. Gordon.
Okay, can I get the proof? You said like suppose there's u that's an M that's not an L,
Right.
and then use algebraic over L. Like, are we always able to like? When are we allowed to assume that there is an algebraic element?
Well, in this particular case, the degree of M over L is finite, right?
Mhm.
That means everything in M is algebraic over L, right? Because
Oh.
all finite extensions are algebraic.
Mhm.
So I could
Oh,
pick
okay.
whatever I want in this case.
So finite implies algebraic, but infinite does not imply transcendental.
No. Yeah, many infinite extensions are algebraic. All right, so, this in tandem with the group theory analogs, lemma gives us the next one, that almost ties everything up for us. Lemma. Place. 13 or 12. Let K inside L inside M inside F be fields, and H and J and Galois group. Okay. And say that H inside J. If L is closed and the degree of M over L is finite, then M is also closed. And you have the equality of the degree of M is closed. And the degree equals the index. Right, and there's an analogous result. If H is closed and the index of H and J is finite. Then J is closed. And okay, so this gets us almost up over one. And finally, if F is finite dimensional in Galois K. In Galois over K. Then all intermediate fields and all subgroups of the Galois group are closed. Fields and subgroups. Galois group are closed. And the degree of the extension F over K is equal to the order of Galois group. It's interesting to note that condition B shows that all finite subgroups of the Galois group are closed. Anyway, and I'm gonna leave this proof, see if you can kind of shuffle in the details, because it's now that we've got those two lemmata from last time, this closes up pretty good. So, right. So this gets us most of what this gets us right here. This gets us most of what we wanted in the fundamental theorem of Galois theory, because we have this business with the interplay between the intermediate fields and the subgroups of G. Just a bit to deal with, and that's the second statement, the one about the normality of E and all that business. So I'm gonna need a definition to, deal with this.
When you say like L is closed, is that like it equals its closure?
No, right, let me remind you what that means. So, call if is an intermediate field using our notation that we have, or subgroup G. We say X is closed if if X is equal to its double prime, right? What we already learned from all that other business was this: X is always contained in its double prime, and we also had that. Right, so if you have an intermediate field that is obtained by priming a group, it's closed. And if you have a subgroup of the Galois group that is obtained by priming a field, it's closed, because when you double close this, it's equal, right? But there may be, fortunately, in our case, if you're finite dimensional in Galois, then all the intermediate fields and all the subgroups of the Galois group actually have this closed property. Definition.
Dr. Cardinal,
Mhm.
what is the motivation for terming it as closed? It's like closed under this priming
It's like,
operation?
yeah, that's right. It's like closed under this operation of double priming. Okay. Let's suppose that, sigma is an element of the Galois group, and E is an intermediate field. Fields. And sigma is in the Galois group of F over K. We say that when E is stable over K, or we say it's a stable intermediate extension. That's what I want to say here. If okay, we say it's stable if whenever you hit E, so you've got this automorphism sigma of all of F. If it pushes E into E for every sigma in the Galois group, we say that it's that the subfield is stable. Let me finish the definition. If you have tau that's in the Galois group of E over K, so here I'm starting with an automorphism of E that fixes K. We say tau is extendable. if there exists sigma in the Galois group of F over K such that sigma restricted to E is precisely tau. So in other words, if we can take tau and grow it to an automorphism of E such that
No.
then we see that it's yes. Notice that it's worth noting here. If tau is extendable to sigma, then the tau, if you can actually extend tau to some sigma, then that tau is well, E is stable with respect to that particular sigma that you extended it to. Right, maybe not to every sigma in the Galois group, but whatever you extended it to, because originally, if you look at sigma acting on E, that's just a restriction tau, which goes into E. Okay, so let me give you an example. So if you look at okay, Q E equal and once again, I'm gonna go back to this great example. Oh, and let E prime. Notice that every then notice that this extension is actually stable, right? Because remember what these automorphisms do, it was just the permutations of this set here. Cube root of 2, omega cube root of 2, and omega bar cube root of 2, or omega squared, however you want to write that. No matter what these do, these automorphisms induce, what does omega do? It either goes to itself, in which case, so when you restrict this automorphism down to Q omega, it either takes omega to itself, in which case this is the identity automorphism extended when restricted down there, or it takes omega to its complex conjugate, right? And the complex conjugate of this guy is still on the field. Notice that omega bar is also in here, right? So no matter what you do, so E prime is stable. E is not stable. Right? Because, for example, if you look at phi 1, 2. This takes cube root of 2 to omega cube root of 2. And I think omega to omega, but it actually doesn't really matter which one. Because in particular, in this case, phi 1, 2 of E is not contained in E. Because it pushes all this real stuff into a field that's got, well, it leaves this, it doesn't put it inside this field. Everybody okay with that? Yes.
Two quick questions. E prime is not a group, is it? You're just using that notation to show that these are.
Oh, I'm sorry, yes, this is not the prime notation that we're using.
And then the other question is that in this case, when you have Q adjoin this root of unity, do you have sigma of E prime is equal to E prime?
Yes, yes, in this case, yeah.
Can you show an example where a stable intermediate isn't like equal?
Yeah, but it would have to be very big. Well, let's see. So if you have an automorphism of the whole thing. No, I guess that should probably be on too, because we'll explore that for a moment. If it's truly stable, then here's what happens. E is stable. So that means that sigma E is contained in E for all sigma in the Galois group. No matter what the fields are, right? As long as it's an intermediate field. Right so far? I claim that this is also one too. So right now, the only thing that's perhaps not clear is this onto, right? So let's let X be an E, right? Well, notice that P inverse V is contained in E as well, right? Because P inverse is also an automorphism. Right. So the inverse of X is Y in E, right?
Yeah.
Therefore, here you go. Makes sense.
Yeah.
So there you go. So this is, it's also on to.
Wait, this is an example of a stable field. What is this?
Yeah, I'm assuming already that this is stable. So what we've proven is, okay, so suppose E is stable. If this is true for every sigma Galois group, then you actually get an equality.
Okay.
Right. Okay, other questions? All right, so here's a lemma that we'll go through. Lemma 14.2.14. Let K inside, E inside F be fields. If E is stable. Then E prime, which is the Galois group of F over E, is normal and Galois group of F over K. And number B, if H is a normal subgroup of the Galois group, then H prime is a stable intermediate extension. So if he is stable, then the prime field, or I'm sorry, when you prime it, that group is a normal subgroup of the Galois group. And on the other hand, if H is a normal subgroup, then its prime is stable. So we will pick this up after the exam. So I will